Mm. Oh, wait. Okay, now someone write in the chat. Yes? Someone write in a chat. Yay! Okay, you can hear. Yay! All right. Okay, don't spam the chat. Okay. All right, folks, so let's get started here. Thank you for joining me at this midterm 1 review session. Does everyone have the packet? You don't have the packet? It was in the link to. Okay, so if you're not in my class, your instructor should have shared a couple links that had the Zoom link and some links for a copy of the packet. I'm working through a packet, all right? So you will be you'll get much more out of this review session if you have the packet. So please get the packet, all right. There's also a key. So there's 2 links. It says like, if your instructor shared the information, it should like Dr.N's gonna work through these 2 packets. Please download these links, and then they're there. I don't know how to share it with you right now, so oh well. Do you have your approved calculator with you? All right, because it's not enough that you can, write all the work down. We also have to work through being able to arrive at the right answer via your calculator. And because a lot of what we work on in this class has to do with, really small numbers, really big numbers. So using exponential notation correctly is really important here. Whoops. And then finally, do you have the supplemental information packet? And that includes the periodic table. So your instructor should have shared that with you. Oh, you guys are sitting next to each other. So cute. All right. And then finally, for folks that are in the chat, make sure that you direct chat questions to everybody, not just me. So in the to line, make sure it says to everybody, not just hosts and panelists, because I will refer to the chat here and answer any questions that are on the chat. All right. And then finally, I am recording right now. The recording will show up on my YouTube channel. Are we all just chatting away? We want this review session to go on. Yeah. Are there concerns? What are we whispering about? No? Okay, just yes. You'll have to just get it from one of your classmates here. I can't spend time and send it to everybody individually. I only have it on my Carmen page, so I'm sorry. Yeah, I would just grab someone and maybe have them email it to you. I guess that's a good solution, right? So why don't you take like 2 minutes to get the packet from someone around you? And I'm gonna drink my LaCroix. Hibiscus, it's my favorite. Yeah. How can I do this? No. You're welcome, Will. Okay. Wow. Okay. So that wasn't recorded. Sorry, guys. Yes. I probably muted myself because I was drinking LaCroix. All right. Sorry about that. You missed all the inspirational stuff I said. So, all right. Let's just start from the beginning then. We have this question. Let's report this expression to the correct number of significant figures. So the idea here, and if you have the key in front of you, that's useful because oftentimes my key will have more hints than I can say like to your face right now. So recognize with significant figure calculations, there's two types. There's addition, subtraction, and there's multiplication and division. Everyone knows the multiplication division one. You just count sig figs, you pick the lowest one. Everyone knows that one. Everyone. It's the addition, subtraction that everyone forgets. And that's usually what changes, gives you a bigger change in the significant figures and maybe how you would arrive at an incorrect answer. So approach significant figures just like you would just put it into your calculator. Like, so if we look here, we see a bunch of operations. We see addition, we see subtraction, we see division, and we see multiplication. So we follow PEMDAS rules. We do everything in the parentheses first. We do the stuff in the parentheses, so the addition, subtraction, and then we do division and multiplication afterwards. So I like to break this up into sections. So if you were going to put this into your calculator, you would figure out, okay, what are those two things added up, right? What are these two things subtracted? And then you would do the multiplication division, right? That's how you would put it in your calculator. You guys usually sit over there. And so it's weird you're over there. Yeah, so whatever. Keeping it light. So yeah, put this in your calculator. All right. So if you put this in your calculator, why can't you hear anything? You can't hear anything? You can hear. Okay, I just have to yell. Should I just put it like right on my face? How about that? How about that? All right, so when we put this into our calculator, what do we get? What does it say? What does it say? Anyone? 8.4. Is that right? No, so let's be a little bit smarter. So I like to tell my students, calculators are dumb. They're dumb. So when we put this into our calculator, we need to recognize that addition, subtraction rules are different. And we oftentimes should go back to third grade and that person might adjust the, okay. Go back to third grade, put the numbers on top of one another and look at the commonplace values. The idea with addition subtraction is that you never, ever, ever count sig figs. You look for commonplace values. What I mean by place values, ones place, the tens place, the tenths place, hundredths place. So both of these numbers go out to what place value? The hundredths or the second decimal place. So that means our answer will go out to the second decimal place. It's not about counting sig figs. It's about looking at commonplace values. So now when we do this, recognize we need to be smarter than our calculator. It's not 8.4, it's 8.40. That last zero is significant that we have certainty out to the hundredths place because our two values we're putting in there go out to the hundredths place. All right, good. So in the parentheses, we have an 8.4 value, or sorry, 8.40 value has 3 sig figs. That'll be useful for us. So let's look at the next parentheses. All right, you can put that into your calculator, but again, I like to just go back to third grade and put those numbers on top of one another. 90.850 minus. So make sure you line up those decimal places. I'll zoom that out. 0.0084. So don't even put that in your calculator. Just look at the place values. Remember, everyone forgets addition, subtraction. look at the place values and look to see where do the common place values end. Both numbers go out to what place value, and they share in common. They go out to the third decimal place. All right, so that means our answer can only go out to the third decimal place. That fourth decimal place, it's going to end up getting rounded away or whatever during the next step. So when you stick that in your calculator, you get something like 90.8416. So for this operation, if we were done, we would round it to 5 significant digits, 90.842. So it would have 5 sig figs. So the idea here is, but we're not done. We're not done. So I actually don't want to round just yet, but I want to keep the idea of where I would have rounded in the next step. Because when we put all of the operations together now, we have, this parentheses, and then we have something down here. Now it's all addition, or sorry, it's all multiplication division. So now at this point, we can just follow multiplication division rules, and it's easier from here. So we got all of the addition subtraction out of the way. We can now focus on multiplication division. So to make it really clear of like what's happening, I'm just going to rewrite everything, without the parentheses. So I have 8.40 times 90.8416, but I would have rounded right there. So I'll underline here my last significant digit. And then finally divided by 2.000 times 10 to the negative 1. All right, so this is all multiplication division. So now it's easy. Now you just count sig figs, just count them. And then you round your answer to the smallest number. Right? So if we inspect all of these values, let me zoom in. This first number has how many sig figs? 3. So that, again, the 0 is significant. If you listen to your calculator, it's dumb. Right? It's dumb. Then the next number has 5. And then what about the bottom number? So this is scientific notation or exponential notation. All of the significant figure information is in what number? The A value or the B value? The A value. So 2.000 has 4 sig figs. This to the negative 1 has no significant figure data. It's actually an exact number because it's literally the number of like times you move the decimal place, and the sign tells you which direction it goes. So I don't like to memorize negative exponent. You move your decimal place left or right. I'm really bad with my lefts and rights. So I just know that negative exponents mean big numbers or small numbers. Small numbers. So I like to rewrite this number as a, I guess, normal notation. All right. So to make 2.000 a smaller number, I'm going to move that decimal place to the left. Yeah, okay, thank you. So it would be 0.2000. I just like to play it safe, all right, when I put that into my calculator to just check that I'm not dividing by 2. I'm actually dividing by 0.2, all right, into my calculator, all right? And so that last one is 4 sig figs. So when we put all that in our calculator, our answer should have how many sig figs? 3, yes. So you put that in, you get a number like 3815.3, okay? And so we just round this number to be 3 sig figs. And so it will be 3,820 or something like that. It probably is best to write it in scientific notation. So 3.82 times 10 to the 123. All right, would be our answer. A common mistake I see students do with really big numbers like this is that they'll oftentimes change the number, all right, to represent 3 sig figs. Sometimes they'll write 382, okay? Okay, you might be giggling and be like, oh, what? I'd never do that. I see it all the time, right? Because doesn't 382, that has 3 sig figs, doesn't it? Yes, but it's a completely different number. All right, so would you rather have $382 or $3,820? It's a difference in value, magnitude But the difference here, or I guess what the similarity is the number of sig figs. So don't change the magnitude with sig figs. So the big idea with this question, addition, subtraction, multiplication, division. There's different rules, all right? That with addition, subtraction, you have to look at the place values in which that they're common. I like to make the example, sometimes I make the example, okay, so like Jeff Bezos is worth like, I don't know, like I'm gonna make up a number, $5 billion. That might be wrong, I don't know. Okay, let's say he's worth $5.1 billion, okay? That's Jeff Bezos. If you took $5 from him, would that change his net worth on Google? No, it would not. Because if we think about place values, because right, if you take $5 from him, that's subtraction, right? If we write out 5 billion, 5, 1, 0, 0, 0, 0, 0, 0, 0, 0. Is that enough zeros? Yes, okay. So if you if you subtract 5, are there any common place values? Are these zeros in the ones place on 5 billion? Are those significant? Are those known? No, they're not. So when you do this subtraction, it's not going to make a dang difference. All right. So when Jeff Bezos goes out and buys like Starbucks, it's not going to make a difference to his net worth. But if I have $26 in my pocket and you take $5 from me, will that make a difference? Yes, it will, because 26, the 6 is known in the ones place. All right. And so if you subtract 5 also in the ones place, that will make a difference. All right. So you're taking cat food right out of my cat's mouths if you take $5 from me. But for Jeff Bezos, it won't make a difference because these zeros at the end there are not significant. Right. Does that stick with you? Okay. Addition, subtraction, different. Multiplication, division, everyone knows that one. All right. Other questions about sig figs? All right. So let's just keep going in order. Okay, so we have a density question here. All right, so I give you the density of aluminum is blah. What is the mass in kilograms of a 64-inch block of aluminum? And I give you the relationship that 1 inch is equal to 2.54 centimeters exact. So there's a lot going on right here. All right, I give you density. The thing about density, some folks, they're like, oh, D equals M over V or whatever. I don't like memorizing equations, right? The unit of density itself gives you the relationship between mass and volume. We are given a volume, albeit like a stupid volume, inches cubed. Who measures things in that unit? And we want to get to a mass in kilograms. So in my class, I like to teach the idea that any unit with a division sign in it, I call that a derived unit, where we can set one thing equal to another thing. All right. So in this case, whatever unit is on the bottom gets an implied 1, and then the other unit up top gets set equal to that. So 2.70 grams of this substance, aluminum, is equal to 1 centimeter cubed. So I took the bottom unit, gave it an implied 1, and the top unit gets the number. I like to give the example. If you are driving 60 miles per hour, so see my unit, mile per hour. If I ask you, if you're driving 60 miles per hour, how far do you go in 1 hour? 60 miles. All right. So this is how I can take any derived unit and turn it into an equality that I can use for dimensional analysis. I like to math my way out of all situations because I don't memorize things. All right. So this relationship will help me do dimensional analysis. So I like to start with what's given. So in this case, they give us a volume. So 64.0 inches cubed. The problem is the density is what gives me the relationship to go from the centimeter cubed realm to the gram realm, the mass realm. But the problem is inches cubed compatible with centimeters cubed? Those aren't the same unit. If I do division here, those units aren't going to cancel. So my idea, I guess my strategy here is I want to start with inches cubed. I need to somehow get to centimeters cubed. My volume, I'll change my volume to centimeters cubed. And then from centimeters cubed, I can use density to get to grams. And then I want something in kilograms. All right. That's my whole strategy. The problem is, and where a lot of students will get stuck on, is this one right here, that first step. How do I go from inches cubed to centimeters cubed? They didn't tell me to memorize that, that equality. But the idea here is I give you inches to centimeters. So literally all you have to do is change inches 3 times. So the equality here comes from the equality that's given. 1 inch equals 2.54 centimeters, but because it's cubed, both sides are cubed. So 1 inch cubed equals 2.54 cubed, and then that has a unit of centimeters cubed. So you don't have to memorize it. It literally comes from the unit itself. Imagine if it was inches squared. If you wanted to go from inches squared to centimeters squared, it's the same idea. It's just, you just square both sides instead. All right, so you start with the conversion you do know and just change it, manipulate it to get, either squared or cubed or, whatever conversion you want. All right, so I'm in inches cubed. I want to get into centimeters cubed. So I'm going to put the 1 inch on the bottom, all right, part of the equality, and 2.54 centimeters up top. Yes. I personally would just memorize that one because that lets you go from metric to imperial. That one, I probably use this one, 1 inch equals 2.54 centimeters. I use the most in my everyday life living on the farm. Because sometimes things are metric, sometimes things are imperial. I would just memorize this one just to cover all your bases. It's not that, yeah. So anyway, how I have this set up right now, do I cancel out all the inches cubed? No, so I have to do it 3 times, 3 times. Yes, 3 times. So now I'm in the unit of inches cubed. So like on the bottom, it would be, or sorry, centimeters cubed. It would be inches cubed. And what I would put in my calculator is times 2.54 cubed. And so the unit that is along with that is centimeters cubed. So that is good because now I can use my equality from density where I will put 1 centimeter cubed on the bottom and then 2.70 grams up top. All right. And that's how I can cancel out my units. Am I done? No, take the half second to reread the question and make sure that you are answering appropriately, because you can go through all the steps 100% exactly right, but you might report the wrong answer or the answer that the question isn't even asking. All right. So in this case, if I stopped right now, I'd be in the unit of grams. I want to get to kilograms. All right. So gram to kilo is something you need to, or sorry, like a base unit to kilo is something you need to memorize. So do we know what the prefix means for kilo? 1,000, but the 1,000 is applied to what? The grams. All right. So the idea here is that 1 kilogram is equal to 1,000 grams. I often see the factor applied to the wrong thing when I check student work. All right. So in this case, 1 kilogram is 1,000 grams. So let me just see if you can't use your intuition here a little bit. When you think about a kilogram, like, do you have an object size in mind? Like a kilogram, it's like a sack of flour or something, like that's a kilogram, right? Half a sack of flour, right? But a gram is like what? Like a couple grains of rice. So what we're saying here is that, a lot of a couple grains of rice is equal to a sack of flour. Because what I oftentimes see is students will write 1,000 kilograms equals 1 gram. That's a common mistake I see. The 1,000 is applied to the wrong thing. But again, use your intuition here. You are trying to make equalities, things that one thing equals something else. So when I write it this way, I hope that your ears ring. Okay, I see this and my ears ring. where I'm like, oh, 1,000 sacks of flour is equal to 1 grain of rice. Like that makes no sense. All right. So then you can revisit those ideas when you have all of your dimensional analysis set up, because oftentimes what happens is that students, they put the wrong thing at the top and the bottom and they don't know why. And so if you see something like that, like 1,000 kilograms is 1 gram, I hope that your ears ring. And it's 1 kilogram is 1,000 grams. So I'm going to put the 1,000 on the bottom and 1 kilogram up top. And now I am done. Okay, now I'm done. So before I give you the answer, can you look at all of this information here and just tell me like how many sig figs you think will be in the answer? 3, yeah. So it's all multiplication division. So we can do the easy rule. We just look and pick the smallest one. So the idea here is that the volume has 3 sig figs. 1 inch to the centimeter is an exact number. So it has infinite sig figs. The density has 3 sig figs. This implied 1 has infinite sig figs. 1 kilogram is 1,000 grams, also infinite sig figs because it's a definition. So we are limited by either the density or the volume. There's 3 sig figs. All right, so use your intuition a little bit. So 2.83 kilograms, go away. Okay, good? Okay, all right, let's go. How many people have taken practice exams? Okay, very good, very good. You know that there's feedback. There's like instant feedback once you submit it, all right? That Dr. Foose has very nice video feedback within there, all right? My suggestion for you at this point in time, just get as many practice problems in as possible. Get familiarized with as many question types, all right? The more you see, the easier it will come to you on the exam, right? Okay. When you do practice exams, and if you recognize like, oh, I cannot get combustion analysis questions, like that's the one you keep misstepping on, at that point, I would go, back to the book or go back to the book or lecture notes to revisit the strategies and then recall, go to the textbook and look at questions relating to that question. Also, another resource for you, if you weren't told this by your instructor, but with the newest edition of the textbook, so we're on edition 15, everyone has access to the e-textbook, okay? It was built into the course fees. If you have access to online homework, you have access to the textbook. At the end of each chapter, chapters 1, 2, and 3, at the end of each chapter, right before the end of chapter exercises, there's a section called exam prep, where there's like 20 to 30 questions that are written like exam type questions. They're all multiple choice. All right. And there's video feedback for those as well. So those are good questions as well, that they're not open response, they're multiple choice. So that's might be something if you're looking for more practice. The exam prep section of the textbook is a good resource for you. Okay, there was a question in regards to the practice exam when it suggests to go to specific. Where are they? Sophia, I don't know because Dr. Foose writes those and I'm not sure. You'll see that once you do questions and if you look at the feedback, certain learning objectives are assessed on those types of questions. So I would look at, other sample exams that have similar types of questions. So I can't answer that specific question because Dr. Foose makes those. All right. Okay. Oh, and then one more thing about the midterm. So I actually haven't looked at the practice exams, the ones on Carmen. Before they were all multiple choice. Are there other exam type questions on the midterms, the samples? Or are they all just multiple choice? Okay, there's some others. Okay, so the exam is, remember, we are limited by a Carmen quiz. So there is no open response. There cannot be open response. So the types of questions you see on these practice midterms will be what you expect on the exam. So I will say the majority of them will be multiple choice. There is some numerical input, all right? Numerical input meaning like for this next question, Usain Bolt sprinting, and I say report your answer to 3 significant figures. I might write report your answer to 1 decimal place. And you would do the math. You would write his speed in, or how long does it take to run a 100-meter dash? You would write the time in seconds to 1 decimal place, numerical input. There's pull down menu. All right, so sometimes like true false questions, there might be a multi-part question in multi-part question in one question. And then what else? I think that's it. Multiple choice, numerical input, and then like pull down menu. Yes. There is no way for us to grade your work. How could, yeah, there's no way. So again, this question, I could write it as a numerical input, report your answer to 1 decimal place. You would just report the answer, right? And usually there's a tolerance. If it's numerical input, there's a tolerance. It'll be like a certain percentage to take care of like rounding, right? So if your like last digit is close, usually it'll take it. So there's that. All right. Oh, what's the question? Fill in the blank. Fill in the blank. There are extended response. I don't know what extended response means. Okay. All right. Yeah. So the question is, do you do your scratch work on the iPad or the scratch paper? So your scratch paper is 2 pages. You're given 2 pieces of paper. The first page is the front side is the periodic table. The back side is the supporting information. So you have at least, I would say, 3 blank pages of scratch paper. So I would bring a pencil with you because you will not be able to write on the iPad at all. Okay. Nothing in this course is curved. There are no assignments that are curved. We grade on a different scale. Okay. All right. All right. Is there a certain question we want to do? Anyone? Just no more dimensional analysis. Okay. So let's do this one. Concepts. All right. So look at these pictures. Let's, so using the following image, answer the questions. So I have pictures A through F. All right. So we need to think about the idea of pure substances, mixtures, compounds, elements. What does that all mean? Right. So which of these pictures depict only one compound? So if you have the key in front of you, I give the tips of how I identify pure substances versus other things. Something's a pure substance if you can represent it with one chemical formula or one symbol. So the 2 types of pure substances are compounds and elements. Elements come off the periodic table. All right, so if you just have helium, that's a pure substance. It happens to also be an element. But if you have sodium chloride, NaCl, that's also one formula. It's also a pure substance because you're representing it with one formula, and that would be a compound. So in this question, which pictures depict only one compound? All right, so the idea here is with a compound is a pure substance, but it's a pure substance that has 2 or more elements bonded together. All right, so we need 2 or more elements. It can't just be helium. It has to be 2 or more elements bonded together. So the idea here is that like these little blocks, blue versus blue and white, those are different elements. So which pictures depict only one compound? So it's only the things that have different atoms bonded together. So I would say this is a compound. That thing I just circled right here, that's a compound. But is that is this sample B, that B box, a pure substance? No, because more than one thing is present. So really the only thing that is a pure substance and a compound would be D. Okay, because we have 2 elements bonded together, 2 different elements bonded together, right? And that's the only thing present in the box. Literally, I just copy and pasted it over and over, right? So it's just D. All right. How come we're allowed only a limited amount of scratch paper? Caden, because There are over 2,000 students taking 1210. So we're trying to limit our consumption of paper. And so having 2 pages, rarely do students encounter running out of space. Okay. All right, so that's one compound. Okay. All right. Related to that, okay, so which pictures depict a pure substance? We have, of pure substance, there's compounds and elements. And again, my tip for students is it's a pure compound if you can represent it with one symbol, one. So the example I give that's a mixture is salt water. Salt water is composed of what? Don't think about it too hard. Salt and water. Salt has the formula NaCl, water has the formula H2O. Those are 2 different formulas. So that's a mixture because you need 2 formulas to represent it. But if you just had water, H2O, or you just had salt, then that would be a pure substance on its own. All right. Okay. So that's my tip. All right. So which ones are pure substances? So basically elements or compounds. So D is one of them because that's a compound. Anything else? Any one of these pictures? A. And specifically A is what? A element or compound? Element. Specific, what, let's extend this even further. What element could that be? Yeah, diatomic. So any one of the diatomics. All right, so it could be oxygen. What's the mnemonic? So which one? Brinkelhoff, whatever that means. Okay. Nitrogen, oxygen, fluorine, chlorine, bromine, all exist as diatomics on Earth. Okay. Yeah, the diatomic molecules are something to memorize, okay, for this class. Because if I say nitrogen gas, you need to know that nitrogen gas on Earth is what formula? N2 gas. It's not N atom. N atom doesn't exist on Earth. It's N2. All right. And then there's hydrogen, and that's it. All right, let's keep going. Which picture depicts a mixture of 2 molecules? Okay, guys, let's bring it back. Okay, which picture depicts a mixture of 2 molecules? So mixture, we know that is represented by, you know, more than one element or more than one chemical formula. But what is it meant by molecule? What's a molecule? Do we know? Is there anything other than a molecule depicted in these pictures? Atoms. Yeah, I heard atom. So for example, that's an atom, right? Because it's just one thing, one building block. We can't make it any simpler. This substance would be a molecule, all right? Molecule, the pictures in E and F are also atoms because they're not bonded together. Here, our diatomic friend is also a molecule. In this case, we just have the same element bonded together. So I guess what's my answer? Which picture depicts a mixture of 2 molecules? Well, so B, I guess, right? B, because it's a mixture. So we need 2 things present, molecules, junk bonded together. C, is that a mixture? Yes, but there's an atom present. All right. What about D? Is that a mixture? No, pure substance. Okay, good. All right. D, what pictures depict a mixture of 2 elements? So A is an element, but there's just one. B is a mixture, but it's an element and a compound. So that's not it. C, a mixture, a compound, and an element. So no. D, just a compound. That's the only thing there. So the only answer is here is E and F. Those are the only substances we have blue atoms and gray atoms, okay, in a mixture. So our answer here is E and F. Okay, so expanding on that, okay, we talked about identifying via the pictures, but can we transform the pictures into one versus the other? Okay, transforming D to F is what? A chemical change or a physical change? So let me erase all this. So transforming D to F, what do we have to do to transform D to F? Break bonds. So is that a chemical change or a physical change? Chemical, because we're literally turning a compound into atoms. So this would be a chemical change. What about E to F? That would be a physical, because what we see here are just like a bunch of these atoms, these mixtures of atoms, they're just changing their relative space from one another, right? So really we're just changing the energy. So that would be a physical change. All right, so, okay, great. Everything in chapter 1, stuff you should work on. I don't know if that's a question. Okay, all right. Any other questions? Does anyone have a request? What? 5? The next one? I don't like that. Okay. All right. Yes. I like to say a molecule is anything that has stuff bonded together. So H2 gas, is there a bond in H2 gas? Yes, so that's a molecule. But is it a compound? Yeah, so that's an element. So the idea here is that molecules can be compounds. Molecules can be elements. So it's like all squares are rectangles, but not all rectangles are squares type thing right now. All right. So if you strictly go by the definition, compounds have to have more than one element present, bonded together. And then molecules just have to have anything bonded together, 2 or more. Yeah. All compounds are molecules asterisks. Yeah. Because in a compound, you have to have A and B bonded together. If a bond is present, then it's a molecule. Yeah? Okay, all right, yeah. All right, let's look at kinetic energy here. Okay, 5 and 7. Let's, which of the following scenarios describes an increase in kinetic energy? So we talked about 2 types of energy in chapter 1, the first being kinetic energy, based upon movement. So the equations here, kinetic energy is 1/2 mv squared, right? The trick for this equation, you use this equation, mass needs to be in the unit of kilograms. Velocity has to be in the unit of meters per second. So that means if I give you the velocity in miles per hour, you might have to convert that before you can plug it into this equation, right? Because in doing this, kilograms and the meters per second, you'll get the unit of joules, which is our SI unit for energy. So what you see here based upon kinetic energy, there's basically 2 ways you can increase kinetic energy, either increase your mass or increase your velocity. That's it. So that's kinetic energy, energy based upon motion. Oftentimes your temperature of your sample is the average kinetic energy of your sample. You know, we think about solids versus gases. We think just based upon particle motion, gases have way more kinetic energy because they're moving much faster. So the one that folks don't like is potential energy. So how we never calculate potential energy. We do kinetic energy. Those are, I'm going to say straightforward because it's plug and chug. You just make sure masses in kilograms, velocities in meters per second, and you plug and chug. But potential energy is tougher because it has to do with electrostatics. Potential energy is proportional to the charges involved, being either attracted or repelled, and the distance between them. So I always like to, in my class, show, you know, the potential energy diagram where we have, this is potential energy. We have repulsions up top and attractions on the bottom. And so this is how potential energy changes based upon ion or particle distance from one another. So this question does not pertain potential energy, but it does pertain to kinetic energy. So make sure you're using the appropriate question, because I could change this question about, okay, how does potential energy change in these scenarios? So, which of the following scenarios describe an increase in kinetic energy? So again, look at the equation here. Select all that, apply. Doubling the velocity of a moving train. So the idea here is velocity is increasing. So does kinetic energy increase? Yes, it does. Doubling the charge of a moving particle. We're doubling what? Are we doubling anything in this equation? No, we're actually doubling Q or something, you know, in potential energy. So does kinetic energy change if we double the charge? No, we don't. That was a trick question. Yes, so nothing changes in terms of kinetic energy, okay? Because we're changing charge. Nothing that affects kinetic. Doubling the temperature of a gas sample of helium. If temperature goes up, imagine in your mind what happens to the particles. Do they? Yeah, they move quicker. So kinetic energy will go up as well. Yes, temperature goes up, your average velocity of those particles increase, so your kinetic energy increases. All right, having the distance between two positively charged particles. Does that change kinetic? No, but does it change potential? Yes, it does. So let's just, for completion, think, how does potential energy change in this last scenario? So if we're having the distance, distance is going up or down? Down, yes, it's going down. Between two positively charged particles. Turn on your monkey brain. If we have two positively charged particles, are they repelling one another or attracted towards one another? Repelling. So if we look at our potential energy diagram here, the x-axis is distance. We are somewhere in the repulsion region because we have two positive charge. So if you go along the graph where distance gets smaller, all right, we're going to go up the curve. Okay, so potential energy is increasing. Again, think about it. We have two negatively charged particles to one another. Think about how they feel repelled to one another. If you bring them closer together, does that repulsion get stronger or weaker? Stronger. So in this case, potential energy increases. All right, but it all has to do with the graph. All right, the positive part of the graph is repulsions. The attractions region is negative. All right, there we go. All right. Okay. 5. All right. Let's just do this one. Okay, 6. So it's the last part of chapter 1. Has to do with accuracy and precision. So my tips here for accuracy and precision, because oftentimes in society, people use those terms interchangeably, but they mean very different things. Accuracy relates to the true value. Oftentimes, like, so we have a bunch of data sets here. What you want to do is compare the average of each data set to the true value. Whoever is whoever's average is closest to the true value will be the most accurate. Precision is about range. So this is more along the lines of student, not user error, but how good the experimenter is. Can they replicate their data, you know, over, I guess, what is this, 3 trials? All right, so this has to do with the user. So you want to look at the range of the measurements. If this was a higher level chemistry class, we would actually look at standard deviation of the measurements, but we never look at too many trials, so range is fine, right? So just looking at the range. But if this was like real chemistry, you would look at standard deviation to compare your precision, right? And so whoever has the smallest range is the most precise. And again, folks, normies on the street use these terms interchangeably, but they're different, okay? And so the idea here is we go back to accuracy. What is the true value in this data set? What's the true value? So here, these students calculated the molar mass of copper. I didn't give you the true value. So can we say anything about accuracy? Why? Yes. So the answer is yes, not because I didn't give it to you, but where can you always find it? The periodic table. So what's implied here is that the true value is coming from the periodic table. What is it? I don't know. 63.55 grams per mole. All right. So I did not give it to you, but because I gave you the identity of the thing, you can get it. All right. So how I approach questions like this is I calculate the average for each student, and then I look at the range. And so the averages, I think it's 63.07, 63.43 for student B, and then 64.23. And so based upon that, student B has the best average. So they are the most accurate. And then I want to look at the range. And so I'll just do the range over here. So for range, I just want to look at the high and the low and then just subtract. So I guess the high is 63.9. There's the low. All right. And so what you see, student A has a freaking huge range. Student B is 0.7, and the range on student C is 0.1. So student C has the best precision. So it's B and then C. But let's pretend, what if I change this question to 3 students conducted an experiment to determine the molar mass of N element. If I change the wording to just, I took out copper and put N element, do the answers change at all? Yeah, so accuracy cannot be, if we don't know what element it is, it means we don't know the true value. So if we don't know the true value, we cannot comment on accuracy, right? So if it was an element, it would be cannot be determined. What about precision? That would stay the same. So that's good and dandy. So the idea here is, I'm sure in your lecturer, they gave the analogy of a dartboard, the dartboard to show accuracy and precision. But the idea is, well, what if you were playing darts not at a dartboard, but you were playing darts at a blank wall, and you had these two students, student A and student B, and they just threw darts at a blank wall. There's no obvious true value, so we can't actually comment on accuracy, but we can comment on precision, and student A is better. Okay, yes. The question is, will the numerical input questions be worth the same amount of points as the other questions? Does anyone have that answer? Yes. All questions are worth the exact same points. Okay. Yes. All right. So let's just keep going. All right. Chapter 1 done. All right. Let's do chapter 2, the idea of isotopes. Okay. This whole idea is that there are oftentimes many stable isotopes of the elements that you see on the periodic table. This is why the masses you see aren't whole numbers. That there's oftentimes some decimal places there because we have to factor in weighted averages. So how we look at isotopes and their isotopic or atomic symbols is oftentimes you have some type of element. You have a number in the top right corner, or sorry, top left corner, and that's your mass number, right? Your mass number is your neutrons plus protons, and then you're based upon the element identity, will tell you how many protons are present. All right. So if you look at my key, I tell you that there are 3 equations to memorize. So just memorize those equations, how mass number is related to protons and neutrons. Protons is related to the identity. And then finally charge, which oftentimes is over here. Charge of your ion or whatever is equal to the number of protons minus the number of electrons. So based upon all this information, we can just figure out the number of protons and electrons and all of these things and then choose the right thing. All right. So yttrium 88. So that 88 is what? The mass number. So that number represents the sum of the protons and the neutrons. All right. So yttrium 88, we get the number of protons from its placement on the periodic table. So yttrium is 39 protons. All right. The number of neutrons will be 88 minus 39, which is 49, I guess. All right. And so the number of electrons, how do we get that? charge. So since no charge is explicitly given, we assume that the charge is 0. So in this case, yttrium 88 is neutral. If I said it was charged, we'd taken that into account, but since it's neutral, there'll be 39 electrons. Okay, strontium 2+. So this is charged. All right, so note here how both of these have 88, but 88 is the mass number. All right, so we are looking for two isotopes that have the same number of electrons. So strontium is 38 protons. All right, and so what we get here is that there are 50 neutrons based upon the mass number, and then the number of electrons. We look at the charge of the substance, and I see, oh, there's a +2 charge. I know electrons are negatively charged, so I know there's going to be less of them. That's how I like to think of it. So there has to be 36 electrons. All right, radium is 88 protons. All right, so how this is given, Ra, I don't even have to actually know the name of it because you can just see it on the periodic table and see how many protons it has. So Ra is not one of the elements that you need to memorize its name, because you can still get all of its information just based upon its the symbol. All right, so 88 protons, and if you do the subtraction from mass number, you get 140 neutrons, and because it's 2+, there's going to be 2 less electrons, so 86. All right, so the trick is that some students, they might mistake, they'll just see, oh, 88, those are the same, but that's not the thing we're looking for. That is the same. We're looking at the number of electrons, which requires us to do a little bit more work. All right, so chlorine has 17 protons, and I'll just do the last one here. Bromine has 35 protons. So going through this, chlorine, if we subtract its mass number here, 36, from the number of protons, there are 19. And because chlorine, assuming it's a charge neutral substance, 17 electrons as well. But bromine, or I guess this would be bromide, calculate the mass number. I guess we don't have to get number of neutrons, but let's just be complete. Yeah, okay. 35 protons. So that means that there's 46 neutrons, because 35 plus 46 is 81. And then the number of electrons. Okay, so if there's a total negative charge, are there more or less electrons than protons? More, so it's 36. So our answer is strontium and the bromine thing. Good? Yeah, so we had to finagle and calculate the number of electrons in all of them. So this is a way we can get you to calculate way more than you need to. Like, you had to calculate the number of subatomic particles in all of them, right? So it's not just like, oh, I ask you, like, what are the subatomic particles in yttrium 88? And you list off the numbers. In this case, because I have 5 different things, it's much harder and requires you to actually calculate all of them and not just one of them. All right, so that's a way we can make questions more difficult. Okay. All right. What's next? Just keep going. All right, what is the chemical formula from the ionic compound formed from the reaction between magnesium and fluorine? Okay, so when naming, I like to think there's 2 categories. There's ionic stuff and there's molecular stuff. Ionic stuff is formed from ions. So the idea here, magnesium fluoride, a compound made from magnesium fluoride, I told you is ionic. So we need to predict what ions are formed in this ionic compound. And so this comes from the periodic table. Magnesium as an ion is always what charge? Ooh, no, Mg2+. Metals, okay, is it on my key? Yes, it's on the key. Metals, their charge, if they're a main group metal, is typically its group number. So that means magnesium, because it's group 2A, is a 2+ cation. Okay, metals form cations, all right? cations are positively charged. We predict cation charge from the group number. Okay, the next thing is fluorine. Fluorine is a metal or a non-metal? Non-metal. Non-metals form anions. Anions are negatively charged. You predict anion charges from the group number, but this time its charge equals group number minus 8. So fluorine is what charge as an ion? -1. So we ask ourselves, okay, how do you combine these two things and make it charge neutral? You need 2 anions because there's only a -1 charge. So this would be MgF2. Right? So at this point, so yes, I figured out the charges, okay? And then when I put together the ionic compound, I can get rid of the charges because you can always predict ion charges based upon these main group elements. For fun, for completion, let's name it. Let's name this. So for ionic compounds, you always name the cation and then the anion. Do you ever say how many ions there are? Is this magnesium difluoride? No, you never, ever, ever have to say how many ions there are because ions are always predictable. You can always predict it. So this is just magnesium fluoride. Magnesium fluoride. All right. So if we look at the answers, it's C. So note how in E, I left the charges. Don't do that. Don't do that. Remember, charges are always predictable based upon the identity of the thing. All right. Let's keep going. Okay. A certain ionic compound possesses this chemical formula. What group number is element X? So the idea here is ionic compounds always, are composed of ions, but they're combined in such a way to be charge neutral. So I tell you here how many cations and how many anions are present. I don't know what X is, but I know what charge is aluminum typically in ionic compounds. 3+, because aluminum is a metal. Metals form cations. Cation charge is predicted from its group number. Aluminum is group 3A. So it's a 3+ cation. But the idea here is that there's 2 of them. So what's the total amount of positive charge coming from cations? +6. So that has to balance out the 3 X anions over here. So from this information, we can figure out what is the charge on X have to be, or of that like missing anion. It has to be 2-. That's the only way to get them to be charge neutral. All right. So then now it's backwards thinking. X 2- isn't the answer. That's not the answer. This question is asking what group number is X-. So we got to go back to the basics. Anions are negatively charged. Okay. Anions are typically made from non-metals. The way we predict charge for negative anions is the group number -8. So the idea here is that what group will form 2- anions? 6A. Yeah, so something like oxide, sulfide, all of those make 2- things. All right. So a common question we like to give is a question like, we give you this compound. Okay, we say, oh, like this compound is that. And then I ask you like, what is the name or what is the formula of like sodium and X put together, right? So you have to like figure out the charge and then charge balance a new substance. That's another way that we can ask this question. All right, so other questions? Is there a question people want me to do? 14. I want to do 13. Okay. I want to do 13. Okay, so which of the following diagrams best represents barium fluoride? Dang. So there's a lot of concepts here. One, barium chloride is what kind of compound? Ionic. How do I know? Barium's a metal. Yeah. So it's ionic. So can't we figure out what the formula is? Yes. So barium, if we look at it on the periodic table, it's in group what? 2A. So barium is Ba 2+. Chloride is our anion. Chloride as a anion is always what charge? Ba minus or Cl minus. So the idea here is that this compound, when formed as an ionic substance, has to be in the ratio BaCl2 of them. All right. So this tells us a little bit about the ratio of atoms that are present, that there's 2 of one, 1 of another. All right. So the idea here is, 1, 2, and 3, all of them have this like 2-to-1 ratio. So that's good. That's good. But there's a big difference between all of these pictures. All right. So the idea here is, okay, so we know that it's barium chloride and it's ionic. Only one of these pictures represents an ionic substance. And this, it's a subtlety, all right? Ionic substances technically are not molecules. Ionic substances, they form this extended lattice of positively charged, what am I doing? Positively charged and negatively charged anions. It's like this extended lattice, all right? Okay. Those are ionic compounds where they're trying to maximize those attractions between ions. Molecular compounds are discrete molecules where you can pick up one of them, like a water molecule. You can just pick up one water molecule. But sodium chloride, you can't actually just pick up one sodium chloride because they're all connected to one another in this like infinite array of oppositely charged particles. So only one of these pictures actually represents an ionic compound. And which one is that? 2. Yeah, so 2 is the right answer. All right. So this one's tricky because 1, like the atom ratio looks right? But what's wrong with this? It's a gas. Are ionic compounds usually gases? No, they're solids. So also it's a discrete molecule. All right, it's also discrete. 3 is wrong as well. The atom ratio is correct. It's 2-to-1. But the problem is do you see discrete molecules? Yes. All right. So if we kind of just take a step back, let's make up substances that would adopt these structures. 2 would be ionic. 1 and 3, these are molecular compounds. So they have to be composed of all nonmetals. So something like H2O. 1 and 3 would be compounds like H2O, right? Where we have 2 of one atom, 1 of another atom. If you want to be really specific, H2O, this one would be H2O, what phase? Gas, all right? And 3 would be H2O. It could be liquid or solid, we don't know, but it's in that condensed phase, yeah, okay? So the difference is there, ionic compounds formed of ions, metal and non-metal, and then molecular compounds, all non-metals. So H2O could be an example, CO2, SO2, also examples, all right, of things that could adopt 1 and 2, or sorry, 1 and 3. And then nothing is 4, those are just like random atoms, yeah. So we're only talking about pure substances. This, yes, could be. If the water molecules, if we mentioned that there were water molecules about, but don't worry about that. All right, save that for chapter 4. All right, someone asked for naming. Okay, so do look at my key and recognize that there's categories. You need to basically identify, are you naming something that's ionic? Are you naming something molecular? Or are you naming an acid, which is kind of tied to ionic naming, even though it's all molecular substances? How do you identify an acid? H, it has to start with H, except water. That's the exception, okay? So yeah, that's basically the process there. So BRCl, let's write the name of this, BRCl. So you identify this as ionic, molecular, or an acid. Is it an acid? No, there's no H. This substance would be molecular because it's all nonmetals. All right, so it's molecular, so we use molecular naming rules. We need to tell the reader exactly how many atoms are present. So you name the first element. If there is more than one of the first element, then you use the prefix. But if it's just mono for the first element, you just say the name. So this is bromine. All right. And then you name the second element with the prefix with an "ide" ending. That's it. You need to tell the reader exactly how many each atom is present with molecular compounds, because you can't predict the number of ions like you would an ionic compound. And that's because there are no ions in molecular compounds. So this would be bromine monochloride, not monochlorine. It's chloride, monochloride. All right. The next one, ZnBr2. What kind of rule scheme is this? Ionic, yes. So under ionic, be careful. Under ionic, you just named the cation and the anion, but if you have to kind of inspect the cation, if it is a variable charge cation, you need to say what charge it is. So that will require you to figure it out, because we know bromide as a anion is always what charge? -1. So that means because there's 2 bromides, zinc has to be +2. But zinc is an exception. It is one of our fixed charge cations. So you don't have to say zinc 2. You don't have to use the stock system. You can just call this zinc bromide. That's it. Not zinc dibromide. Di is only used in molecular compounds. Because you know zinc is always a 2+ cation, you should know that zinc bromide is ZnBr2. Okay. Titanium, on the other hand, is a variable charge cation, all right, because it's kind of like in the middle of the transition metals here. So we need to figure out what the charge of that titanium is and tell the reader exactly what charge it is. So we have to use the anion to help us. The anion here, SO4, 1 is what polyatomic anion that you should have memorized, and what charge is it? Sulfate, and it's 2-. So SO4 2-. So the idea here is there's 2 sulfates. So what's the charge of titanium have to be? Try again. 4, yes. So 4. All right. I love the stock system because you don't even have to think about it. You just call this titanium 4 sulfate. The Roman numeral literally tells you what the charge is for that cation. So you only have to do that for variable charge stuff, because titanium 4 exists, titanium 2 exists. You need to tell the reader exactly what it is, because both of those things have different formulas. But if it's something like in group 1 or 2, those always have predictable charges, so you don't need to use the stock system. All right. All right. Why does zinc not get a Roman numeral? Because it's an exception. All right, let's do some of these. Okay, sulfur tetrafluoride. What is it? It's a molecular, so it's S, F, 4 of them. That's it. Okay. Ammonium phosphate. Ammonium is one of the polyatomics that cations that you need to memorize. Do we remember what that is? NH4, what's the charge? Plus, and then phosphate is PO4 3-. So here's the idea with ionic substances. This is why you don't need to ever say how many of the cations and anions there are, because as long as you know the charge, the idea is you always put them together to be charge neutral. So the idea here is, can I put these 1-to-1 with one another and be charge neutral? No, I need 3 cations present. So NH4, 3 of them, PO4, that's it. All right. So here's a trick idea for you. So this is an ionic compound, right? We used ionic naming rules, right? But where's the metal? Aren't these all nonmetals? I thought Dr.N, you said all nonmetals are molecular compounds. What's the difference here? They're polyatomic ions. So ions are present. So that's why it's ionic. All right. Okay. Yttrium 3 sulfide, like before. I love the stock system because it literally tells you what the charge is. What's the charge of yttrium? 3+. And then sulfide as an anion, S2-. So this is yttrium. I think you need 2 of them, S, 3 of them. So this is why you don't have to say yttrium, diyttrium, trisulfide. You don't have to, because as long as you know the charges. Yeah. The last one of 11. Okay, fine. Okay, yeah, the 2 acids. All right, so acid naming rules. Here's my trick. Listen up. My trick. So both of these are acids, right? Both of these are acids. Longer the formula, shorter the name. So short formula, long name. So both of these are acids. Identify what anion is present. So what's the anion right here? Nitrate. What's the anion right here? Sulfide. So the idea here, H2S is a really short formula. The anion is really simple. It's monoatomic. It's going to have a really long name. That's where you include the hydro. All right. So the idea here is HCl, really short name. That's hydrochloric acid versus something like HClO3. ClO3 that's chlorate. The name of that acid, HClO3, is chloric acid. So HCl, hydrochloric acid, long name, short formula. HClO3, long formula, short name, chloric acid. All right, so using those ideas here, nitrate, it's a polyatomic, it's going to have a short name. So what would this be called? Eights become X, us, or ites become us. So this is nitric acid. What about H2S? Hydrosulfuric acid. Hydrosulfuric acid. What is sulfuric acid? Yeah, so sulfuric acid is the acid that's attached to sulfate. So think to yourself, okay, sulfate is SO4, 2-. How many H pluses do you got to slap on that to be charge neutral? 2 of them. So I don't like to memorize. Okay. So instead of memorizing charges of polyatomics, I like to memorize the acid. All right. So like H2SO4, because there's 2 hydrogens, I know that that's a 2-. But something like H3PO4, PO4 has what charge? 3-. Okay. And so forth. Yeah, lots of questions. Yeah, what's up? Oh, what did I write? Whoops. Okay. Okay, my key is wrong. Okay, so H2SO4 is sulfuric acid. Yes. Okay, let's go. All right. All right, with that in mind, remember long name, usually a short formula. So hydroiodic acid would be what? HI. Iodic acid would be something with a iodine with a polyatomic. All right. Okay. Okay. Hypochlorous acid. So this one has a long name, but it's not the hydro thing. So we have to inspect the polyatomic that's attached here. So let's take it backwards. Us acid is ite, right? So if we kind of take it back and figure out what the polyatomic is, we can figure out what the name is. So us is ite, and then we just attach the rest. So we need to figure out what is hypochlorite. So how I like to memorize this, and you know I hate memorizing, so I memorize as little as possible. I know that chlorate, I like to call it the parent polyatomic, 8, chlorate, nitrate, sulfate, phosphate. All of those have certain formulas, and depending if there's more or less oxygens than the parent, you change the ending or suffix, all right? And there's rules on that, just read the book. So in this case, ite means that we're one less than chlorate, but then the hypo says that we're an additional oxygen less than chlorate, all right? So the idea here is ClO3 is chlorate, ClO2 minus is chlorite. So that means that ClO, one of them is hypo chlorite, right? So that means that this substance, ClO minus, that's our anion that we care about. So hypochlorous acid is HClO. Okay, so that's removing oxygens. What if we added an oxygen to chlorate? Per, you add per. Yes, all right. Okay, cool. All right, as long as it's not a fire alarm. Okay, great. All right, what other questions? Okay, I think someone said 14. Okay, so let's do 14. The idea here is, okay, let's combust ethanol. So ethanol is one of the, this is actually a combination of chapter 2 and 3, because ethanol is one of the simple organic molecules that we have you built. All right, so there is something you need to memorize within organic compounds. And the idea here is that based upon the number of carbons in the chain, gives you a different parent name. So F means how many carbons? 2 carbons. So the idea here, meth is 1 carbon, F2, prop 3, but 4. And I think that's all you need to memorize. Yeah. It's one of the names. It's just, it falls under a different category of naming that we've used. Ethanol is not like ionic or molecular compounds that we've been naming before. So technically ethanol is still a molecule, but it's more complex than just binary molecular naming. So we use a different naming scheme. All right. Okay, so ethanol has 2 carbons. So my strategy here is I connect those 2 carbons. What's special about carbon? It always forms 4 bonds. So if we wanted ethane, we just add a bunch of hydrogens. So in this example, like in order to write a balanced equation, I need to know how many atoms are present in the molecule. Do you want to memorize the number of carbons and hydrogens in ethanol? No. So my strategy here is, as long as you know how to build it, you can figure out what the formula is. No, you don't want to memorize it. You don't want to memorize it. So the idea here, if this was ethane, the formula would be C2H6, yes. But this is ethanol. So the difference is we replace one of the hydrogens with a OH. Okay, all right, just like that, all right? And that oxygen and hydrogen is bonded to one another, all right? So you'll see it like that. All right. So this is an instance, it pays off to know how to build it, all right? Know how to build it, because from that you can get the formula. So you can see that the formula is C2, H, 5 of them, OH. All right. So now the idea is we need to combust it. Now that we have the formula, we can combust it. So again, don't memorize these, just know how to build them. That's much more important here. So the idea with combustion, and this is how we ask combustion questions, all right? Because a combustion question, it's going to require you to fill in like 4 different coefficients, right? So the way we get around it is we ask you, report the sum of all of the coefficients, because there's still a lot of places for you to screw up if you report the sum. So to combust the thing, we have to react this with oxygen. This is just the definition of combustion. And then what are our 2 products? CO2 and water. The states don't matter because we're just balancing it. So who cares? So my strategy to balance combustion reactions, so you will always be right. Step 1 is you balance carbons with CO2. Step 2 is you balance hydrogens with water. Step 3 is what I like to call you take inventory of your oxygens on your product side, and you count them up, and then you adjust the coefficient in front of O2 to make it match, the both sides match. And then if there's a fraction in front of O2, you multiply everything by 2. And if you do it that way, you will always be right, all right? Because the idea here is like, we save oxygen to balance for last because oxygen shows up 2 places on CO2 and water. It shows up in 2 places. So if you balance oxygen first and then you balance carbons, you'll mess up your oxygens anyway and have to revisit it. So when you save really simple things for last, it saves you from doing this like dance of you keep messing your count up. All right, so let's do this. Balance your carbons with CO2. So let's put a 2 coefficient in front of CO2. Next, we balance hydrogens. How many hydrogens are there on the reactant side? 6. So do note that that oxygen's tacked on at the end there. So what's the coefficient in front of water? Is it 6? No, it is 3. All right. And this is the tough thing with oxygen. This is what I like to do. And if you do it this way, you'll always be right. We're done with the product side, right? There's coefficients. There's nothing more you can change. So what I do is count up all the oxygens on the product side. How many oxygens are coming from CO2? 4. How many oxygens are coming from water? 3. So there's a total of 7. So then I ask myself, how can I make sure that there's 7 oxygens on my reactant side? But there's a little bit of trouble here because oxygen shows up in 2 places, but that's okay. How many oxygens are coming from ethanol? 1. So 1 plus what equals 7? 6. So how can I get 6 oxygens? 3, and that's it. Okay. So if we were to report the sum, what would it be? The sum would be, yes, 9, because I see how I didn't put a coefficient in front of the thing I was burning, but what's implied? A 1. So it's 1 plus 3 plus 2 plus 3. Okay, what's next? Let's just do the next one. Okay, which of the following represents a decomposition of a molecular compound? Okay, so decomposition, what's the thing to look for? Breaking apart one reactant, many products. So I think right off the bat, you can like eliminate a lot of these, right? Okay. But then, so we're looking for a decomposition. So the thing I'm looking for is one reactant, many products. But I give you a qualifier here. It has to be a decomposition, but also of a molecular compound. So molecular compounds are composed of all non-metals. Okay. So the idea here, A, is that a decomposition reaction? Yes, it is. It is. There's one thing, aluminum oxide. Yes, there happens to be 2 of them, but that's okay. It's just one thing. And it's decomposing into many other things. That's a decomposition reaction. But is it of a molecular compound? No, it's of an ionic compound. So this is how we can ask 2 things at once. This is where you screw up. All right, so all the words here matter. All right, so A is not correct. Yes, it's a decomposition, but it's of an ionic compound. All right, B, is that a decomposition reaction? Heck no. What is it for fun? Combustion of what substance? Do we know what CH4 is? It is methane. Yeah, so based upon our small organic molecule naming, ethane, 2 carbons, methane, 1 carbon. Okay. C, is that a decomposition reaction? Yes, it is. We have one substance H2O2 decomposing into water and oxygen. So is that our answer? Yes, because H2O2, is that molecular? Heck yeah, it is. Hydrogens and oxygens are nonmetals. Okay, let's, for fun, what's D? D is what kind of reaction? Combination. Yeah, so one product being formed from many reactants. A combination reaction forming what kind of compound? Ionic, molecular, an acid, molecular. All right. All right. 22. Okay. Fine. Okay. We're moving along. Okay, we'll just skip to chapter 3. So using the balanced equation, answer these questions. So there are the weights for you. When 25 grams of magnesium reacts with aluminum chloride, how much aluminum solid is produced in grams? And so the idea here is we are given amounts of both of the reactants. All right. So using stoichiometry, I can figure out if all of that magnesium is converted, reacts and becomes product, I can figure out how much stuff I make. But the problem is I give you magnesium and aluminum chloride, both of those reactants. I don't know which one runs out first. So the best thing to do is just calculate both. You do stoichiometry setups of both, where you start with gram amounts of, your starting material. So in this case, magnesium. In order to use the balanced equation and the coefficient, what unit do you have to be in? Moles. Moles of stuff is your ticket to use those coefficients. So I'm going to go from grams of magnesium to moles of magnesium. Once I'm in moles of magnesium, I can use the coefficients and get to moles of junk that I want. In this case, it's aluminum. All right, so then I go to moles of aluminum, and then finally grams of aluminum. That's the process. Grams, moles, grams. You're going to do that a billion times in this class, 1220, organic chemistry. All right. So to get from grams to moles, what piece of information do I use? Atomic mass or molar mass, specifically because we can turn gram amounts to mole amounts. So let's set this up. Basically, my strategy here is I'm pretending, okay, all that magnesium reacts. How much junk do I make? All of that aluminum chloride reacts. How much junk do I make? And compare those numbers. So 25 grams of magnesium is what we start with. So I give you the atomic mass of magnesium. So 24.31. The unit of molar mass is what? Grams per mole. Go to bed tonight and in your sleep, say the unit of molar mass is grams per mole, grams per mole, grams per mole. So that means 24.31 grams per mole. If we want to write that as an equality to relate gram amount of magnesium to mole amount of magnesium, we just say 24.31 grams of magnesium equals what? The bottom unit with an implied 1. So 1 mole of magnesium. So that's how the molar mass is useful to us in a conversion. And so that allows us to multiply by some fraction so we can convert. So that 24 number, is that going to go on the top or the bottom? Bottom. Do I have to memorize that? No, you inspect the units. So 24.31 grams goes on the bottom, 1 mole of magnesium goes up top. So now that I'm in the mole of unit of magnesium, moles of magnesium, I can use the balanced chemical equation, okay, and the coefficients. I want to get to aluminum. I want to know like how much aluminum I would make. So I can make another equality based upon the coefficients where 3 moles of magnesium equals 2 moles of aluminum. Where did those numbers come from? 3 and 2. The coefficients. So now look at the unit. If we go back to our work, we're in the unit of moles of magnesium. So am I going to put this 3 on the top or the bottom? Top or bottom? Bottom, because the unit is 3 moles of magnesium. So I put moles of magnesium on the bottom, and then 2 moles of aluminum up top, And then finally, get gram amount of aluminum. So I use the molar mass, which is given right here. So again, remember 26.98 grams per mole. So it's 26.98 grams of aluminum is 1 mole of aluminum, and that equals something, whatever it is. And so then we do it again, but for the other reactant. All right, so we start with 55 grams of aluminum chloride. Right? So you may be I don't think, is there anyone in the audience who can just look at these amounts, 25 grams of magnesium, 55 grams of aluminum, and know what the limiting reactant is? No, you can't. You might think it's magnesium because there's less of it, maybe, but that's not the correct way to go about it. All right, and that's probably wrong too. Yeah, actually aluminum chloride is our limiting reactant. So we start with 55 grams of aluminum chloride. Do I put 24 grams on the bottom? 24.31? No, we want to use the molar mass of aluminum chloride. So we use aluminum chloride. Do I give that? It's 133. So 133.34, 1 mole of aluminum chloride. So now that I'm in the unit of moles of aluminum chloride, I can get on the bus, use the balanced chemical equation however I want. So what you see here, 2 moles of aluminum chloride is 2 moles of just straight up aluminum. So it's just a 2-to-2 ratio, 2 moles. So like one mole of aluminum chloride, 2 moles of aluminum chloride, 2 moles of aluminum. And then finally, I'm just going to convert to mass because that's what I want to report. So 1 mole of aluminum, 26.98 grams of aluminum. So there we go. Those are my 2 setups. For both, I did grams to moles to moles to grams. For both of them, I used the respective molar masses for each. All right. And so what we calculate here, if you put that into your calculator, you see if all of the if all of the magnesium reacts, we get 18.5 grams of aluminum. If all of the aluminum chloride reacts, we get 11.1 grams of aluminum. Which number is more important to us? The smaller number, because that's the amount we actually produce. This is 11.1. This is our theoretical yield, because what this is implying is that aluminum chloride makes less of the reactant, so that's going to run out first. And so that means aluminum chloride is our limiting reactant. All right. And magnesium is in excess. All right. So what is this? How much aluminum solid is produced in grams? 11.1. That's how much we make. All right. So the great thing about the limiting reactant is when that is consumed, if that's completely consumed, it's the moles of the limiting reactant is what dictates how much product we make and how much reactant we consume, because that dives into the next question. If these 2 things completely react, how much of the excess reactant remains in grams? So just based upon our information we got, which reactant is in excess? Magnesium, all right? Because we already identified, okay, aluminum chloride made the smallest amount. That's what's going to get completely consumed. Magnesium is in excess. So that means at the end of the reaction, when aluminum chloride's all gobbled up, there's still going to be some magnesium left. So to figure out how much is left, we're basically going to do stoichiometry again. But the idea is we need to start with an amount, the right amount. The idea here is that the limiting reactant gets consumed. Completely consumed. So if all of the aluminum chloride reacts, we can figure out via stoichiometry how much magnesium also reacts. So trying to change up this strategy here, we're starting with grams of aluminum chloride because that's limiting. That is what's dictating how much stuff things are consumed or produced. We want to go to moles of aluminum chloride of our limiting reactant. We then want to go to moles of magnesium. That's stoichiometry, right? And then we want to go to grams of magnesium, and this will be what is consumed. All right. So basically the question, it's going to start off exactly the same as over here. We're assuming all 55 grams of this aluminum chloride is reacting. All right, so now that we're in moles of aluminum chloride, if we go back up to the balanced chemical equation, we see it's a 2-to-3 ratio. So that means every 2 moles of aluminum chloride react, 3 moles of magnesium react. Now we want to figure out how many grams of grams of magnesium react. So we use the molar mass of magnesium, because we're in the unit of moles of magnesium. And so the information's given. Moles of magnesium is 24.31 grams. All right, so plugging this into your calculator, what I just said is I'm assuming I'll erase all this, okay? Okay, go away. Okay, let me just zoom up here. We know that aluminum chloride is limiting. Okay, that's a limiting. So the idea is I know how many moles of aluminum chloride I have. That's going to dictate how much magnesium I consume. That's what I'm calculating right now. Again, using the gram to mole to gram, strategy, but we need to make sure that we start with the right amount and we're going to the right amount. So when you stick that into your calculator, you get that 15.04 grams of magnesium is consumed. Is that the answer we want? No, because what is the question asking? Not how much is consumed, but how much is left over. All right, so the idea here is we started with magnesium, how much? 25 grams, okay? So, 25 minus 15, there should be about 10 grams of magnesium left there, all right? Okay, so if you picked the wrong limiting reactant, if you said magnesium was limiting and you went on and figured out, okay, how much aluminum chloride was in excess, you would actually get a negative number for aluminum chloride, and that can't be right. That you would have to consume more aluminum chloride than you actually started with. And I hope at that point your ears are ringing and you recognize that there's something messed up there. All right, so the dimensional analysis got us an answer, but not quite the answer we wanted in terms of the question here. So read the question. Yeah, so if you did a BCA table, it'll also get you the same answer, okay? Because the change line in a BCA table is dictated by stoichiometry. All right, so really stoichiometry, does this look any different than the dimensional analysis we did in chapter 1? No, it doesn't. It's just a bunch of fractions that we cancel the units out, okay? I treat everything as dimensional analysis, everything. Okay. What? What number? Okay, let's do 22. Okay. So we do this reaction with 76% yield and we collect that much junk. How much magnesium in grams must have reacted? So it's this equation again, we're relating aluminum this time to magnesium, all right? So the idea is, okay, this reaction has 76% yield. Do you remember what the equation is for percent yield? Actual over theoretical times 100, whatever. So 8.95, is that actual or theoretical? That's actual, all right? So the idea here is, well, if I only get 76% of the solid, do I need to aim for more or less of the product when like calculating how much stuff I need to start with? I need to aim for more. All right, so the idea here is if I want 8.95 grams of aluminum, I need to figure out what my theoretical yield is. It has to be a bigger number. All right, I need to aim for more than 9 grams. I need more. So as a fraction, 76% is 0.76. So what we get here is that my theoretical yield, what I need to aim for is a number. I need to aim for 11.78 grams of aluminum. That's what I need to aim for, all right? Because I don't get it all back. I need to aim for more. And so this is the number I'm going to start with to do stoichiometry. So remember, stoichiometry, we start with a gram amount of something. We go to a mole amount of something. We go to a mole amount of something else. And then finally, a gram amount of something else. So let's make sure we approach this in the most like deliberate way. We right now have a theoretical yield of aluminum. So I basically know how much aluminum I'm starting with. So if I convert aluminum to moles, I can then go to moles of magnesium and then moles to magnesium and then grams of magnesium. So the question is, how did I get theoretical yield? I did some math like that. I don't teach math. I moved that over here. I did 8.95 divided by 0.76. That's what I did, I think. Is that what I did? Yeah, okay. That's how you calculate theoretical yield. But again, use your intuition here, right? Like we only get 76% of our product, so we need to aim higher. So if you get a number, like if you accidentally multiply by 76% and you get like, I don't know, like 6 grams, right? That doesn't make sense. Oh, shoot for 6 grams, you're going to get more than you put in. Like that doesn't make sense. All right. So in this case, we need to aim higher. Okay. So theoretical yield. So it's the same instance as before. So 6.78 grams of aluminum. We need to convert that to moles of aluminum. So 26.98 grams, 1 mole AL. Then you do stoichiometry. So literally this is the exact same stuff as before. Moles of aluminum. Then what's the ratio? 2 to 3. So 2 moles of aluminum, 3 moles of magnesium. And then finally, just convert that to grams. 1 mole of magnesium is 24.31 grams. And so what you get is that you need to start with 15.9 grams of magnesium. All right. So the idea here, if you kind of want to work backwards, all right, how to check yourself is basically, you know, apply all the information we just used. Assume all 16 grams of magnesium reacts, figure out how much aluminum you make, apply the 76% yield that you only get 76% of it. You should get that 9 grams at the end. That's what you should get at the end. All right, so you can kind of work in the forward direction because that's a little bit more intuitive. All right, so I want to do 23 because I'll tell you a story. When I was a graduate student here, so I like finished my undergrad, came to graduate school here. They gave us a Gen Chem. They gave us a Gen Chem final. As graduate students, like we weren't students anymore. They gave us the Gen Chem final, but it was all conceptual questions, all of them. So they even said, you don't even need a calculator to do this exam, all right? And I don't know, I wanted to like show off and like do really well, okay? And I did do really well, but I got one question wrong. And it was this one. It was this question I got wrong. Okay, so let's do it, all right? For nostalgia. So don't get this question wrong. That's what I'm saying. Don't get this question wrong. So here's a reaction. All right. 1 chlorine, 3 fluorines, 2 these. What's the name of this? Chlorine trifluoride. Yeah, because it's all nonmetal, so it's chlorine trifluoride. Okay, so this is what the contents of your container is, and we want to describe what does it look like after completion of this reaction. There's a couple ways to do this. All right, so one way you could do a BCA table. Do you want to do a BCA table? No. Okay. All right. Okay. So another way to do it is recognize. Okay. I need to consume a chlorine molecule, but then how many fluorines do I also need to consume? 3. 1, 2, 3. So if I draw an arrow, I do the reaction once. So what do I make in that process? If I consume everything on the reactant side once, I make 2 ClF3s, right? What's the detail here? So I did the reaction once, but what else is also in the container? The excess stuff I didn't touch. So there's 2 F2s still in the container. All right. So you need to look at these pictures and ask which one fits that afterline. The answer is D. All right. So if you said A, that's what I said. That's what I said, you know, like 6 years, or I don't know how many years ago. I said A. It's not A because the idea, I asked you right at the beginning, how do you name ClF3? You said chlorine trifluoride. So that is what kind of thing? Molecular. So molecular compounds are molecules. So what you see here, this thing, this is ClF3. This is not what ClF3 looks like. So when I say we make 2 chlorine trifluorides, I literally mean we make 2 molecules of it. We don't make it bonded together. And that's the mistake I made. That's the mistake I made. I forgot that these 2 compounds, because that 2 is there, I don't know what I was thinking. But ClF3 is a molecule, so they are separate. Okay, so just for completion, I don't care what you say. I'm going to do a BCA table because I want to show you what the BCA table looks like as well. All right, and how it can completely describe what's going on. So 2 ClF3. So BCA stands for before, change, and after. So all we have to do with this equation is fill in what does the container look like in the before line. So ask yourself, how many chlorine molecules are there? 1, 2, 3. So 3. How many fluorine molecules are there? 3. How many ClF3s are there? 0. So my reaction has to go forward. And so the idea here is, can you tell what is going to run out first? The fluorine is going to run out first. So that's going to be our limiting reactant. So limiting reactants get consumed. So I'm going to subtract 3. So we completely consume the limiting reactant. Do you see that? Okay. So I identified the limiting reactant. So within the change line is dictated by stoichiometry. So if I consume 3 fluorines, how many chlorines do I also consume? Just 1. Is it +1 or -1? Minus. What about ClF3s? If I consume 3 fluorines, how many chlorines chlorine trifluorides do I make? +2. And a way to do that is look at stoichiometry. So if I have 3 F2s, look at the stoichiometry. For every 3 F2s, you make 2 ClF2s. So 3 F2s, 2 ClF3s, sorry, and then cancel that out. So you see that you produce 2 chlorine trifluorides. So it's all dictated by the coefficients, the stoichiometry. So now you just fill in the BCA table and you see, okay, after the reaction's done, 3 minus 1, there should be 2 chlorines left in the box. Then you add the ClF3s, there should be 2 ClF3s in the box. So you pick the picture that shows that, and that would be D, because ClF3 is a molecule, a discrete molecule. Yeah. So here, how I got these 3s, I looked at the picture. There's 3 chlorines, there's 3 fluorines. So here, I just used my intuition. I thought fluorine is consumed 3 times as fast because there is equal amounts. Fluorine's gonna run out first. Or if you do this and you think chlorine's gonna be the limiting reactant, just try it and you'll get negative numbers. All right. So yeah. Okay. Any last questions? Because I want to be done. Okay. All right. Let's just be done. What? Good luck.